Anyone? I'll just name the new entrants. Arun,
Yes sir.
have you seen the videos?
यस सर, मैंने तो जो आपने 2 लेक्चर्स अपलोड किए हैं वो तो मैंने देखे हैं, अभी 50% कंप्लीट हो गए हैं। उसमें कुछ नई चीज़ है तो उसको समझ में टाइम लग रहा है थोड़ा। यस सर।
Jayashree,
Yes, sir.
have you seen those videos?
Yes, sir. First class, I have seen, sir. First class.
What about the second one?
Second one, just now before this class, I watched that first class, sir. After this, I will watch the basics one.
Okay, so there are 2 videos. Okay, those you
Yes,
should
sir.
download it and at least go through those 2 videos. I'll try to revise as much as possible so that you should also follow the content. But there is one more advice, that do not, leave any classes. I mean, just continuously you have to attend the classes, because this course, there is one only major limitation is, once you absent in any one of classes, the content goes from far more ahead, because we have a 2-hour session. So frankly speaking, at least 1.5 hour we discuss about the content, rest half an hour we'll discuss about the questions and discussion part. But in those 1.5 hour, content goes very far ahead and it is very difficult to follow. Fortunately you have recording, but sometimes what happened, that the classroom discussion is much more healthier. Okay. So do not try to leave any classes as much as possible, so that would be much more beneficial. Okay, coming
Okay.
back to another, I'm just sharing the slide. Okay. Just wait a minute.
I hope the screen is visible to you. Let me just go back to the slide. So we were discussing about the representation of random variables. Obviously, just to quickly revise you with the original discussion part, that we go into the field and collect the data, collect the measurements of all possible variable that is available to us, that our instrument can measure, be it length, width, whatever we were discussing, angles, linear measurement particularly, and angular measurements. So that was the original discussion, that as part of Geo-Informatics professional job, we have to go to the field and we have to collect all possible linear measurements as well as angular measurements, be it length or angles, vertical angles, horizontal distance, vertical distance, whatever it is, we have to measure it with the help of instrument. And when we do so, what is really happening? We collect huge number of data, isn't it? Data in terms of numerical values. And when these numerical values come to us, we know that since it has been captured by instrument and humans have captured it, it is a possibility that there would be certain sources of errors in the data set. So we discussed about the types and sources of errors, and majorly we discussed about that there are three sources of errors. Also, there are three types of error, rather I would say. One is gross errors, blunders or mistakes. Then we discussed about the so-called systematic error. Then we discussed about the random errors. So in blunders and mistakes, we discussed that it should be avoided. Such type of observation should be avoided, which contains such kind of errors. And in systematic nature, which is we also called as bias. Bias is a more technical word because we fall in intellectual category kind of people. We are generally biased towards any kind of discussion or any kind of facts and figures. So in similarly here, observation also follow the mathematical aspect of bias. So those errors which follow a mathematical certain mathematical model, we call those errors as a systematic error. Okay, and similarly in these cases we try to use those models to avoid those errors. But what is more important is that the errors of what should I say, the random nature which is bound to happen. You cannot probably avoid it because it is by nature it would occur. Okay, and when it will occur, you will have less control over it. To avoid it, rather you will have to devise mechanism by which you could minimize it or reduce it. So that was the original discussion. That's why we have started this unit of discussion. And in fact, I have uploaded the syllabus also for this course, which you people can refer and try to see the content which we are going to cover in this particular unit. But more importantly, we discuss about the concept. We started with this unit as concepts of measurement and errors. So yes, it is true that random errors are primary our attraction, that we have to devise mechanism by which we have to avoid it and reduce it. Then we realize that since random error doesn't follow any kind of mathematical model, what we know of about these errors is that they have frequency of occurrence. The positive aspect of random errors is that they have probability equal occurring in positive side as well as negative side. So that helps us in dealing with the theory of random errors, that we devise or think of certain probability models where we try to discuss those distribution which appropriately behave in a similar manner like our random errors are behaving. So that was our objective, to moving from core mathematical background towards this probability understanding. That's why we discussed about the basics of probability, and gradually we discussed about the probability distributions, and started from very basic. We knew what is probability distribution function and what is cumulative distribution function. So that was the two discussion part that has happened in the last class, that probability distribution function, where instead we started with this discrete random variables. The objective was very simple, that how the smooth curve of a probability distribution was achieved in the case of continuous random variable. So it started with discrete. In discrete, we have seen the histogram nature of the distribution, and once the data is increased to a larger side, that same histogram converges to a smooth curve, which represented the scenario of random variables. And that is the basic understanding we discussed in last class, that this probability distribution function, which consists of the random variable and its distribution function, that represent the random value or random error. Similarly, we also discussed that since we know that random errors doesn't follow any kind of mathematical distribution, okay, so we discussed that since they have frequency of occurrence, so how can we use this frequency of occurrence in order to answer certain questions? The questions are simple, that what is the probability that random error will fall between this and this, what is the probability that random error will be more than this, what is the probability that random error will be more than this, like that. So this was our objective, to pick up those questions and try to answer it. And most probably many of you have started the assignment part, which is very simple. In fact, if you try to solve those examples of chapter 5 of Mikhail and Gracie book, you would see that majority of questions are same. Only thing is the function is changed sometime, or maybe a few more subsections of questions are attached. So it is good that you should first read the book, the chapter 5 and chapter 1, before starting with the assignment. So what will happen, your understanding would also improve, okay? Because these kind of it is not expected, as well as not possible, that in these 2 hours I will tell you everything what is written in the book. We discuss as a classroom session, we discuss about some important points, but for your own understanding. In fact, when I was learning from this course at IIT Kanpur in 2010, I found very difficult. The only reason it was difficult because I was not following from the book. I was only focused in the classroom. And at classroom, sometimes what happens, if you miss 2-3 points, critical points, you cannot learn the 4th or 5th point. Okay. So what is really benefited to me was that I just followed the book, and it gave me a little more satisfaction that I followed the book and the classroom together somehow. So that's how I will also suggest you that you should also follow the book. That would be much more helpful to you, rather than thinking only that classroom would help you. It's not possible. At a PG level, the spoon feeding is severely avoided. Okay, it is not BTech that every time a teacher would give you something, then you would only read that part and then jump to examination. No, in PG level, it is highly expected that you complement the teacher just by exploring much more independent content rather than depending only on the classroom. So that would be initial suggestion to you, that you start following the books, start following the content, extra content which is given to you in terms of lecture notes, in terms of reference papers, and in terms of certain books. Okay, coming back to our discussion, just a moment. Yes, so representation of RV. I don't know whether slide is visible or not. Anyone?
No, sir.
No, sir.
Yeah, I got it. Just a moment. Sumit, I assign this responsibility to you. Whenever the slide or audio is not coming properly, then you please inform me. Okay.
Sure, sir. Okay.
Okay, so the representation of RV, obviously we discussed about the certain aspect of it, and we answered this part of question, is that what is the probability that X will fall between A and B. And we also discussed that in the case of continuous random variable, where you will have certain distribution, there is a lesser advantage would be given to the equality sign. Instead, we answer this as probability of X as a random variable falling between A and B. And in fact, this is the answer for discussion part which we have done. That probability of X is equal to B would be 0, because you cannot differentiate between what would be the probability before and what would be the probability after it. So yes, the small f would be represented with the probability density function, yani ki small PDF. Okay, that is small PDF, and capital F would be CDF, or probability distribution function. So that is the one aspect of previously we have discussed this part also, that both are will be correlated to each other, and in fact understanding of one could be improved after other. Okay, so this was how we are representing a random variable. Okay, and in fact we have discussed this part in the case of discrete also, as well as in the case of continuous also. Okay, I hope some of you have already gone through the content, but as a classroom we have to take care of all the students, so please bear with it. Just take a revision of it, and then we'll quickly go ahead with today's class. So in this case of discrete RV, we know that the summation sign is a representation of uh, the so-called the discrete nature of the variable, where we have to take the sum of all random variables in that distribution function. So here
Excuse
the
me, sir.
fx, yes,
Sir, sir, the green part is very small. It is visible little bit less. Can it be
it's
zoomed?
not visible
Sir,
now.
it
It's
is visible,
visible
but nice. Yes, yes. Sir.
Sir, please rotate the screen. So
now.
it will be helpful.
Now it is visible.
Yes, sir.
Okay, so what I was discussing is that in the case of uh, random variable, we have to write fx xk, and the answer of the right would be given by the left. What is the answer? What is the question of the right? What is the probability that x would take a value as xk? That would be given by putting up the function or evaluating the function at this value of xk. And in fact, sum of all the probabilities associated with it would be 1. That is the concept of probability. Similarly, the cumulative distribution function, the so-called associated distribution function, would have been answered in a similar fashion, but slightly deviation between these two. One could easily see the deviation between these two is that here and here you have the probability that x is taking this value as xk, but here what you are answering, that probability that x is taking value less than this xk. Why? The reason is simple. The reason is simple because in the cumulative function, I'm just discussing the continuous nature. I'm not discussing the discrete nature right now. See, in the case of small fx and in the case of capital fx, the difference is simple, that here you will have such kind of function. So here it is the curve which is representing the individual frequency of occurrence, or you could also call it the probability of occurrence of individual event. So in the ordinate you will have the values of probability, maybe y is equal to fx. Okay, but here you have summation of all probabilities associated previously, and it would be added up and put it up here in the case of cumulative. That's why these there are two different questions are being asked from two different functions. So in the case of probability density function, you are answering this question: what is the probability that x as a random variable would take a value as small xk? However, in the case of CDF, you have, or CDF, or in case you will also call it PDF, the probability density function. What we are answering, what is the probability that x as a random variable taking value less than or equal to xk? Okay, so this is how the both two are interrelated, and I guess one someone has suggested to rotate the screen. Just let me rotate the screen so it will be helpful. Mhm. Rotation is off. Okay. Is it better now?
Yes, sir. Now better.
So let me just get a bit. Okay. So we were discussing about similar nature of the continuous random variable, and in the case of continuous, you could see that we are trying to answer the similar properties just like in the case of discrete one with the continuous nature. That obviously in the case of fx, the so-called the probability function which is always positive, that is the for all x, that is representing wherever your x is, be it in positive side or be it in a negative side, your for all x the function value is always positive. It's very important to understand, okay, that we have discussed in fact last class also. Many of students have asked the question on this same. So, and in the second is that if you consider the probability from both end, minus infinity to plus infinity, the summation of all probability, that is integral, because in the case of continuous curve, you go with the integral rather than summation sign, and this integral is 1. Okay, these are the some of the basic features of your probability density function. And in fact, if you have to evaluate the probability between any point A and B, you will try to integrate like this. Okay, integrate the PDF. Obviously, first step, let me just quickly go and tell you. The importance is that first you should know the PDF. What is PDF? If you do not know the PDF, you cannot answer anything. So first objective is whenever you see any problem, whenever you see any kind of measurements, and you have to answer about the probability of occurrence of various kind of random errors, you first have to look for the PDF. Or if you do not have the PDF, you try to see whether it is following the bell-shaped curve or not, so that you could use the popular bell-shaped curve data. Or if it is not the bell-shaped curve, you could in any kind of discipline, you will have different kind of flavor of data set, the behavior of the data set. Obviously, you would choose the other PDFs. So, but let's say if it is a bell-shaped function, you are already aware of the function PDF, and I'll quickly jump to that also. But if you see the data set, and if you are aware of it because it is written in any question, you should check the PDF, and then you will try to understand the problems. What has been asked? If it is asked that what is the probability that x would take value between A to B, then obviously you would answer with it this integral kind of thing. So it is that value from A to B, that fx dx. Now you just have to integrate it and you will get the value. Similarly, you have the cumulative distribution function, which is taking values less than a particular value. That's like this one. We have function capital Fx xk, that is the probability of x taking value less than or equal to xk. And in that case, you have to take the answer from the minus infinity to x, and then you will like. Why? Because cumulative function, you have to consider all previous x before answering this particular probability, which is that x is taking value less than or equal to x. See, this is the figure. So in the case, this is your cumulative distribution function for random variable, and you have to answer it. Let's say for this part, if you are answering for this part, what you are trying to do? You are trying to answer that what is the probability that x would take value less than or equal to x. You would have to answer about this reason. Similarly, you would have the ordinates for C, you will have the FC values, and you would have answer for. Similarly, one could see that deviating from one distribution function to other. Sometimes what happens, the cumulative probability values or cumulative frequency values are tabulated. It is given in a tabular form to you, and what will happen? What will happen? That you will have to choose the values, okay? And when you choose these values, then there is a chance that you do not have to go for every time you do not have to integrate it, okay? What you will do, in fact, you will use those tabulated values to answer it. So that is one way of understanding, okay? More details would be available in the video, which you could go through. This is one example for PDF of continuous random variable. Again, the same thing, where fx indicates the probability density function such that the probability that a measurement falls between two values x1 and x2 would be given by the shaded area, and we have to integrate it. Similarly, like the way we are writing it in the green box, the integration of y dx. Okay, normal distribution curve. Again, I was discussing about the just before the bell-shaped curve, because in the case your bell-shaped curve will be defined by this very popular function 1 by sigma root 2 pi exponential minus x minus mu square upon 2 sigma square. So the continuous nature of this normal distribution curve is very popular for our Geo-Informatics discipline. Okay, in our Geo-Informatics, majority of the data fall in this category of normal distribution curve, which is represented by, it's very good important point which may not have been discussed previously. It is represented by n within bracket will write mu and sigma square. So it is represented by n mu comma sigma square. So mu would be defined as the mean and sigma square would be defined as the variance. So that's how you represent your normal distribution curve. So if in any literature, if it is written as n as 2 comma 8, so this will represent that you will have a data which has a mean value of 2 and a variance value of 8 that you have to work with. Okay. Again, mu and sigma are the mean and standard deviation. Sigma square is the variance. That's a relation between variance and standard deviation. Okay. So yes, again, if you have to construct the corresponding CDF, so this is the PDF. Okay, this is the PDF, a small PDF, and if you have to construct the corresponding CDF, obviously it will be of a continuous nature, okay, like this, increasing, always increasing. Okay, that we have discussed in the last class. These are the certain properties which we discussed. Now you can follow from the books in terms of examples more about it. Okay, the normal distribution curve with mu is equal to 0. This is a classical example of normal distribution curve to explain the random errors, or in fact Gaussian law for random errors. That will come later on, but eventually that starts from here. The background starts from here. That what is the discussion related to the mu is equal to 0. What will happen, and when this will case happen, when you will have a mean as 0. Now this is very important point. Just discuss it before going further, because that was not discussed in the previous class. So what is really happening, if you have measured the so-called length, okay, length of a table, length of anything, okay, then what is expected from the observation? So obviously we'll discuss about the expectation in detail, but here we introduce the term expectation. I'm just writing. Expectation operator. Now, what is the difference between expectation and estimation? Now, do not get confused between these two terms. One is expectation and another is estimation. Both are far different from each other. Expectation comes first. Expectation comes first. What is expectation? That is by the word itself. What is expected from the observation? So when you measure any length, any angular measurement, what is expected from it? That it would give you the true value, isn't it? Initially, what is expected? If you go ahead and take the measurement, what would be the true value of that measurement? That would be given. Okay. So if length is of 100 meter, by manufacturer, they devised or they give you that this length of the table of length of a particular entity is 100 meter. What is expected from any independent measurement that has been collected from any kind of instrument, that every measurement would approach or true value? But from our first discussion, it is very well clear that true value is not known. You do not know the true value. Instead, what is really happening? You know the most probable value. Okay. What is the most probable value? Most probable value is the mean. Okay, which out of 100 observation you have taken the mean. So since you do not know the true value, what you will do generally? You will generally go ahead with the so-called most probable value, and that is mean. So what is expected from the observation? Let me just change the color so that would be much more. Take it as red. So what is expected from so-called what is expected from your individual measurement? That it would approach the so-called mean value, isn't it? If you have collected any data, okay, if you collect any data, what is expected from your individual measurement? That it would go and, or in fact, it would be the mean of the all possible measurement, isn't it? And what do you expect from its error? Because obviously every such measurement would have certain error associated with it. Now here I'm not talking about the, obviously I'm not talking about the mistakes and systematic error, because obviously those errors are not dealt with there any kind of probability models. So here we are only talking about the random errors. So what is expected from the so-called error part of it? So let's say if you have any observation Li, it would have associated error considering the random nature. So this error, what do you expect? That obviously if it is error, it should also approach the mean of the error. This is the mean of the error, mu e, which in fact you want as 0. This was the basis why we started the discussion of mu is equal to 0, because many of you would consider this as an extended case, isn't it? Because we have just discussed the bell-shaped curve. You know the formula, you know the function name, 1 upon sigma root 2 pi exponential 1 minus 1 by 2 x minus mu by sigma square. So that's how you remember it. But we just going ahead and giving the mu as 0. But why? What is the reason for it? This is the reason. Because ultimately we have to apply it over the cases of various questions that has been put up for answering the probability of occurrence of random errors. Okay, there is a difference between these two things. Initially you would have observations, then you would have probability distribution of the random errors. तो अभी हमें यहाँ पर we are answering about the occurrence of the random error, and here we know that it is expected that from any kind of error it should be 0. Okay, so that's why the case of mu is equal to 0 is put up. Once you put up the case of mu is equal to 0, that's why you solve this area under the curve. Similarly, 1 upon sigma root 2 pi exponential minus x square upon 2 sigma square. Okay, because mu has become 0. Now you would have only the deviation associated with it, because if your error is there, that would be associated with various kind of deviations. Okay, now probability of event, probability of a single discrete event occurring at x can be obtained by defining a very small region, infinitely small, under the event, and compute the area of the region. Okay, similarly, these are the properties. I'm not going through it because these are the extended properties. You will take help from the basic calculus, 11th level calculus, and you will try to solve these partial derivatives, single derivative, double derivatives. Okay, and then you try to see what will happen if we go with the putting up these properties and try to understand what would eventually come out. Okay, so yes. Now, what is the direction for further moving ahead? In this slide, we have seen that the by observation that the maximum value of y occurs at when x is 0, isn't it? When x is 0, that is you would achieve the maximum value of x, and that has become the sigma 1 upon sigma root 2 pi. Okay, so as sigma goes to 0, y becomes larger, it is higher probability, and smaller sigma means more precise data, and higher probability, that sample means is good estimate for the population. Okay, so in future, what you want, okay, because now you are exposed to bell-shaped curve, now you know how to find out the probabilities, and probably by next week you would solve too many examples and exercises that would give you much more exposure towards solving those problems. But how do you want to go ahead? Because you cannot do every time just go and start the integral portion of it. You cannot solve every time integral of it, isn't it? Because that is not our job. As part of Geo-Informatics professional, we need to be capable of certain alternatives, because our task is not here to prove our mathematics nature. Instead, we need to solve the problems, the questions that have been asked. So for that, what is really happening, since it is not possible that you you cannot solve every time integrals, so what is expected, that you would devise something. What has been devised? This has been devised, the standard normal distribution table, that has been devised. Now, objective is simple, that instead of solving every problem right from very beginning of integral from minus x to x, sorry, minus a to b, minus infinity to x, instead of that, you devise a table and a transformation mechanism. If you do that, you will be happy to know that by doing these two, that you know transformation of a variable, if a normal variable to standard normal variable, and a table to help you. What will happen? Your computational effort would go down. Okay, that is the objective. So you know about the normal distribution, that of all existing probability distribution, this one is more important, your normal distribution, okay, and that has various application in any kind of SNT application. But this is a very complex model. To integrate every time, it would be a challenging task, okay. So in order to do so, that you know in order to solve the questions put up every time, you would convert this or you would find a new random variable z, a new random variable which is denoted by z in majority of the reference books. This random variable is said to have standard normal distribution if and only if the mean is 0, the population for which you are trying to find out the uh, normal distribution, standard normal distribution, where it belongs. So it belongs to a population, obviously, because every time you have to devise the new variable, okay. So new variable would be associated to a population, isn't it? In the last class also we discussed that in a class you have to pick up the populations. That population would be in hundreds. If 1,000 of a class is there, you would pick up the population, pick up the sample from 100. But whatever you do, you pick a sample or you work with a population, every time you discuss about a variable, it would be associated with a corresponding population. So here also, when your job is to devise a new random variable which you are denoting as z, it would be also be associated to a population which needs to have a mean and variance. So this standard normal distribution or standard normal variable belongs to a population whose mean is 0 and variance of 1. Okay, so this random variable z is said to have standard normal distribution if or belongs to a population whose mean is 0 and variance is 1. Now your job is, now you know the probability distribution function of random variables or normal distribution function. You have to convert it by putting x as mean as 0 and sigma as 1. Now just give me answer how your uh, normal distribution would look like. I'm just going back to your previous function. Let me just quickly go to that. Yeah, this is your function, let's say. This is your function, okay? Now putting up the value of mu as 0 and sigma as 1, what will happen? What will happen? Your function would become 1 upon root 2 pi, because sigma is 1. 1 upon root 2 pi exponential minus, do not say x, because now it is not x, it is a small z, because you have just uh, um, uh, you know devised a new random variable which is z.
Excuse me, sir.
So this z, yes.
Excuse me, sir. Sir, one boy,
Yeah.
Arun Sani, he has been thrown out of the team, so because he has put some cancel button. So he's requesting to add him by your side. He has messaged me.
Okay, just a moment. Why?
Arun Kumar Sani.
Just a minute. Arun,
Yes, sir, Arun.
is not responding. Actually, he has joined the other meeting. That's why nobody is there. Okay, coming back to your original discussion. So now this standard normal distribution which we were discussing, what is really happening is that now your function has become, instead of again I am also writing like that, instead of fx it has become now fz. Okay, and this fz is equal to nothing but 1 upon root 2 pi square root 2 pi exponential minus z square by 2. This is your standard normal distribution, where z is obviously minus infinity to. How this function has been obtained? This function is obtained from normal density function, the previous equation, by setting mu as 0 and sigma as 1. This is you could call it as a special case of previous function, and it provides you a very computationally easy way of evaluating the probabilities associated with any normal distribution. Okay, you cannot integrate every time, but again the question remains how to convert x, your original problem random variable, to z, isn't it? Because you have devised a new random variable, that is fine. You could convert it to, you can make it z, you can make it x, so you can make it y, you can make it t or anything. But how to convert from x to z? That is one more question. You have to answer it right now, because the questions are not put up in terms of uh, solve it only by standard normal distribution or solve it only by, questions are questions. You have to answer it, answer the probability levels. But what you have to do, you have to convert the your original random variable to standard normal distribution variable, or standard normal variable, pardon me. So what has happened? A table has been introduced, and this table is given at the last of Mikhail and Gracie book that you could follow. And there is also Wolf and Gilani book, which is another book which I'll upload soon. And there also in these pages, this standard normal distribution table is available for all possible values. Okay. So in that table, what is really happening? All values from minus infinity to that t is given, and t is known as a critical value which you would evaluate. And uh, since this whole area under the curve should be 1, the values are between the area under the curve should be 1, so that we have to see when we try to solve similar kind of problems. Okay, so how to convert x from z? Okay, so in order to convert from x to z, you have to find a function of like this, isn't it? If you have to convert x from z, you have to write a function like that. That function is nothing but x minus mu by sigma. In your original problem, you would be given a data set having mean and having your so-called sigma. Just by putting this mu and sigma here, your conversion from x to z would be easily given. Okay. Again, here in this bottom, what we have done, we have converted the original random variable x, or this process is also called as standardization. Okay, in this in the process of transformation, this is by conception, this problem is known as transformation. problem of x conversion of x to z. So in this process, what we have done, we have converted x to z by one transformation, which is known as capital Z as x minus mu by sigma. Mu as mean, sigma as standard deviation. Okay. Now coming back to again the same problem, that if your z is now x minus mu by sigma, what would be the resulting function? Now what we were answering from our cumulative distribution function, that probability that z would take a value from less than or equal to z, small z, would be given by a capital phi z. We obviously, if you want to write it as fz, that would be okay, but please understand we are slightly deviating from original notation. That's why we are using phi, and to be consistent with the literature also, this is again I am writing, this is your CDF, okay, the cumulative distribution function. And what we generally do in order to find the cumulative distribution function, we try to integrate our original function, which is this fz, isn't it? We write fz dz like that, okay. But here it is capital Z less than equal to Z. It means what is the probability that standard normal variable capital Z take a value less than or equal to Z? The integration would be minus infinity to Z. Okay. So that's how you, and that is for all Z from minus infinity to plus. That is way you can write the function, but obviously this has been tabulated. The integral which is we are writing is evaluated and is presented in a table. Please remember the the values in the table is of cumulative distribution function. Many a times people get confused. Every year student get confused. This value is what? Distribution function or density function. So as I've explained by this function nomenclature, that you are integrating it. The moment you are integrating something, it is you are going into the domain of cumulative distribution function. So this table is standardized table and it is applied to every problem. Okay. Similarly, what we are writing in the previous slide, same is explained here. This is your x minus mu by sigma, y minus y by sigma. Any could, you could choose any variable. You could choose y, you could choose x, the prime variables. Okay. So let's say problem is given. Okay. Problem is, I hope everybody would be having your pen and paper with them or note sheet. Just simply think that your x is a normally distributed random variable, the primary one, x. I'm not here differentiating between standard normal variable and random variable. You just have to read the problem. That let x be a normally distributed random variable with any kind of mean and sigma. Okay, it could be anything. It could be 100. It could be maybe 9, something like that. So you have a primary random variable mu as this and sigma as 9. Now my question is, what is again, what is probability that x would take a value less than or equal to 10? What is the probability that x would take a value between less than or equal to maybe 70, like that? I will ask input of this question. So you should remember that in your Z, in formation of Z, you have, you know the mu, you know the sigma, but what is X? X is this individual questions that are put up. Because eventually X is a random variable that is going to take a value small x, isn't it? So the corresponding random variable, if this is going to take value as a small x, this would become small z. That's it. Simple. Isn't it? So if you want to put up the 70, okay, so you put up the 70 minus 100 upon 9, like that. So for computational point of view, you have to change the values to be much more easier. Okay. So with these kind of problems, you would have to go ahead with the solving many more problems. But please remember that this is your basic function. This is the individually asked values in different types of probability question. That is the sigma and mu would be given. The moment you give this x as a small x as a value, or any kind of numerical value, 10, 12, 15, 20, for any purpose of solving the probability, this z would lead to, immediately would lead to small z. Okay. Where this is used, analyze the statistical difference of variables, check data for blunders, outliers, mistakes. See, this is one threshold or one way you could eliminate the blunders, outliers, and mistakes. For any kind of answers which we were looking for from this problem, we have to look for the table. For example, like this one, we know how to write it. We know the probability of z, small z, taking value less than or equal to t would be given by nzt. Because in previously what we have written, in the previous slide we have written probability z taking value less than small z would be represented by phi, your so-called the z, isn't it? Similarly here, if you are taking value z as t, so from table you have to find the value of this particular t. That table you have to follow for solving the corresponding problem. But few alternatives to determine what if the z is between a and b, again, because you have a cumulative function value, you have the values in this table, you will choose that value. And that this table is given at the end of Mikhail and Gracie and other books if you have to follow it. Okay. So let's say I'm giving one problem, okay, to solve for you people. See whether you could attempt it or not. So if your mu, is 12 and sigma is 2, You have to answer the probability that x is less than 10, x is between 11 and 15, and x is greater than 16. These are the three questions that has asked. X is a random, normally distributed random variable with mu as 12, sigma as 2. Use your normal distribution table and evaluate the probability that x is going to take value less than or equal to 10, between 11 and 15, and greater than 16. Now, before jumping to the table directly, just look at how you would approach this problem, isn't it? Just wait for a minute. Try to write it first. So let's say for the first, we are writing probability x is less than 10. You have to convert x. This is x and this is small x. Similarly, you have to convert. So the moment you convert x to z, how would you write x minus mu, which is 12, by sigma, which is 2, less than or equal to which value? 10 minus 12 by 2. It becomes probability z less than or equal to minus 1. Now probability of z less than equal to minus 1 would become phi minus 1. If you go now to the table and try to see what is the value of phi minus 1, you would be given a value of 0.1587. Similarly, the other one, what is the probability that x would take a value between 11 and 15? On both sides, you will apply the standardization. 11 minus 12 by 2, x minus mu by sigma, or rather you would simply put the values x minus 12 by 2 as 15 minus 12 by 2. That becomes probability of, here it would become how much? 0.5. To 1.5. Now here it has become the case probability of z between A and B. Probability of z become A and B would be nothing but, would be answered from cumulative distribution function value B minus cumulative distribution function value at A. So you will write as phi 1.5 minus phi 0.5. From table you get the values like that. Now similarly try to solve the third one. What is the probability that x is taking value 16? Just attempt it. Try to write it at least once. Anyone that could attempt this problem? How would you write? It is one
So
way of.
5 of minus 5.
greater than 2.
Sorry, say again.
So you asked this last value, which is in 5 terms.
Hmm.
5 of minus
Say
5.
again, what would be the 5 of minus?
5.
No, why would 5? Again, you try to see the way writing the
So 5 of
probability
2.
x getting
5 of 2.
5 of so how you would write the probability of x greater than 6? So you would write, since the reason is simple, that in cumulative case your function value would start from this ordinate 0 to infinity, let's say. So for infinity value, what is the value? 1. That means for if your distribution doesn't have anything further, or if you have to answer it for any value of more than greater than a particular value, it would be included in all this curve. So if this is how you are writing, so x would be written as 16 to infinity, then your phi would be written as infinity minus phi of small z corresponding to 16 को आप represent कर सकते हैं 2 से. मैंने वो step गायब कर दिया है जिसमें 16 2 बन जाएगा. So phi infinity is 1 minus phi 2 is from the table, whatever it is would be answer. Okay. See, you have to attempt a lot more problems to get comfortable with. The only issue is with this is your practice. The more you solve 2-3 more problems, you will be comfortable with this probability computation. It's not difficult. The objective was to introduce you to the standard normal distribution. The whole theory behind discussion of is to how you should be familiar with the standard normal distribution, because our job is not to integrate it. Every time the function would be given to us, there would be some solution, we have to use it. So the probability model is always behave the actual observation, isn't it? You have the model with you that would behave the actual scenario. Okay. So coming back to Gauss law of accidental errors, that is our next discussion. So accidental or random errors, they follow Gauss law of accidental errors. Obviously, Gauss law of accidental errors have certain properties which we'll discuss. And the deviation of above equations, which we discussed, is based on probability theory with following 3 rules, which is small errors are more frequent then large errors. Positive and negative errors are equally likely. Very large errors do not occur at all. So this is we are the three rules which we are talking is because we understood by the concept that outliers are gone, systematic errors are gone. We are not considering these two. Otherwise, this if you are considering systematic nature, very large error would also be a chance. If you are sorry, if we pardon me, if we consider the outlier, if you do not remove outlier from equation, then what will happen? Very large error will occur. Okay. If we do not remove systematic error from the equation, chances of positive and negative are less likely, because in systematic nature either the errors would be in positive side or in the negative side. The only case where these rules will apply if the outliers, blunders or mistakes and systematic errors are removed or taken care of, then only these three rules would apply on random errors. And in fact, the theory of estimation, the course, this geospatial data analysis, adjustment computation, parameter estimation, all this problem is because of random errors. It is not because of the systematic errors. It is because of the random errors is there in the picture. That's why we are trying to estimate the parameters with the observable which is having random errors. So in fact, if you talk about the overall summary, what we are doing, we are estimating the parameters. We are estimating the parameters with the help of observables. With the help of observables. As I've told you in the first class, observations and observable. The difference between observation and observables are observations that are itself is a variable because they contain the random errors. So you are estimating the parameters. You are estimating the parameters from observables. That's why this whole process is discussed under this theory called estimation theory, parameter estimation, and adjustment computation in other names. Okay. So with this, we stop here. If you have any questions, maybe previous two classes also, if you have any question, those who have attempted the problem might be occurring certain. Yes.
Hello, sir.
Yes.
Sir, in assignment 2, question number 9, I think there is a problem with it.
What is assignment 2? It is matrix assignment.
Yes, sir.
You just write it to me in the message on Teams. What do you find as a problem? Okay.
Okay,
That
sir.
has been prepared by one TA. Maybe something has been misspelled, or maybe just write it back to me. I'll try to see. Just 1 minute. Just 1 minute. I'll just. Who is speaking right now? May I know the name?
Sir, Alok Kumar.
Alok. So just Alok, you just write it back to me. I'll reply you back. Okay.
Okay, sir.
But it's good that you have started the matrix. Algebra part of assignment. It's very. It is very recommended, highly recommended, that you all should go and try to follow the basics. I have uploaded 2 books. This is just to remind you that I have uploaded 2 books. One is Mikhail and Gracie, and there is another one by professor from British Columbia. I just forgot the name. But those 2 books have appendixes and in fact a chapter on matrix basics. So if you do not follow the content by supplementary item which is uploaded in the assignment tab. You can go through the books also. Objective is very simple, because just after this unit which we are discussing right now, we will quickly switch on to adjustment part, and there you will have to solve the problem by solving various matrix related issues, and then you will realize that there is a chance that you will feel little difficult something if you do not follow the matrix algebra. So I just suggest that everyone should go and try to read, at least devote certain time to your basic mathematics, back to basics. That would help you. Okay. Yeah. Anyone else? Abhijit.
Sir, assignment which we have to submit on 9th. So we have to do examples or the exercises at the back.
See, objective is that you at least first attempt the examples, then you go back to exercises. Okay. Example and exercise. Do not write the questions on your answer sheet. Just simply start answering it, attempting it. Previously, many students have written the whole questions, but there is no need of it. Okay, you simply start answering it. Objective is that you should attempt it.
So sir, both examples and exercises.
Yes, both. आलोक, आप मुझे वो वापस लिख के भेजिए जो भी प्रॉब्लम है स्पेसिफिकली. I'll revert it back. Okay. Anyone else?
Sir.
Okay, for tomorrow, as I've told you, and I'm again repeating, that tomorrow is your laboratory for basically it was a laboratory dedicated for exposure to instruments, but since due to pandemic the actual field work cannot be done. So what I've given as a task, that initially you should read the module or listen the module 1 and module 2, and I've also given the link. So tomorrow we will discuss on all 6 lectures, and it is expected that everyone should prepare at least 1 page of individual lecture as a summary, the key points. It is not as you write the paragraphs. You should write in terms of bullets what you understood. So just by listening it, you have Word file with you. You can open your laptop, you can open in the Word file, you can write the points in terms of bullets points, what you understood from those lectures. So 10 or 15 points from each lecture would be expected. So everyone would be invited, and he would just sum up for what they have read, what they have listened, in fact, from that lecture. So what would happen from one point of discussion, we will cover individually the whole essence of the mapping purpose. Then gradually we will discuss the other aspects once you will finish those basics. Objective was simple, that you should have little exposure to the basics of topographical mapping before coming to the instruments. But since instrument would be, we would give you a little demo of the instrument through virtual mode. But before that, it is advisable that you should follow those lectures. So tomorrow it is expected that every one of you should be coming with your 1-page summary of all 6 lectures. So those who have not listened it, try to listen it today and tomorrow. So we'll meet at 3 p.m. Okay. Any more questions?